Are there any questions? So let me double check, make sure the streaming is on and with the voice. Okay. That's not good. Uh-oh. That's my point. There we go. I might need to do this again because it is recording. Oh, it's recording just fine. It's just that the initial location of OBS is off. That's why we couldn't see it. Okay, that's fine. And we got Firefox also moved to someplace else on the screen, so let's move it back here. And now it's over here. Something doesn't seem right to me. But OBS still seems to be recording just fine, so we'll say that this is okay. Alright, so it's just wider than usual. It's not the default. Okay. Alrighty. Look at this. And where's my browser? Need to move that one more time. There we go. Okay. Alright, so what we will do today is to answer any questions that you might have about the first exam, which is on Thursday, which is the day after tomorrow. So if you have any questions about the double representation, because that's also your homework, okay? So we need to address that first. So I hope that you guys know that we have a homework assignment on double conversion, because we talked about it. I presented the program that you start off with. So let's do that first, just so that we all understand this part. This is my Monday, Wednesday class. They won't let me change the tiles to reflect, to use whatever nickname I want to give to a class. So I have to remember which class has this particular number. And the homework is here. It is double conversion, and it's due on Thursday. Is that okay? Okay. I'm pretty sure we talked about this last Thursday. No?
No, I thought it was due today.
Oh, it wasn't. It's not due today. It's due on Thursday.
It was originally, but then you changed it.
Okay.
So.
Yeah, I changed it because I forgot to put it on Canvas. So I decided, okay, we'll put it on Canvas, and we'll start 1 week from the time that I put it on Canvas. So if you get it done today, it's good. You just it's the same amount of work, right? You got it done already. You don't have to worry about it. If you are still working on it, you have 2 more days to get it done. If you have questions about it, today would be a good day to ask. Yes.
It's due before class, right? It's due before class.
It is due before class, so that would be due right before the exam itself, which I think is good because when you're doing this homework assignment, especially the last part, it has to help you study for the double representation, because that is what you need to get that last part done. Okay. So are there any questions about the double representation? I can go through examples in class, if that is needed. If not, yeah, go ahead.
Like, how do you, actually, no, I'm figure it out.
Okay,
Yeah.
that's fine, not a problem. So any questions about the double representation?
Can you just show us some examples?
Okay, some more examples, sure. All right, so we'll go ahead and, go ahead.
Can you actually add mantissa 2 and exponent 2 for the structure?
Yes, you can modify the structure itself. I don't think it's necessary to modify the structure because it has its own variables to track and whatnot. But if you want to add additional members to the structure, go ahead. Because I'm not.
It makes itself convenient.
If you use subroutines, yes, because you have everything packaged or encapsulated into a single structure. Yeah, so go ahead. You can make your own structure too. You can define your own structure and pass a pointer to an object of that structure if you want to, or you can extend the one that is already there. Okay. All right, so getting back to examples, okay? So what we'll do is, since I got my document camera here, so the first thing is to revisit what it looks like. Okay, so we'll go to document camera, and yeah, unfortunately Linux does not have a driver for Elmo, which is the document camera, the super expensive one that the school has bought. But I can't use it because there's no driver for it. It's USB, but it doesn't like to talk in a way that Linux understands. And this is what I don't understand, is how come they do not open source the driver? Okay, what does this company has to lose to open source their driver? Okay, they're not going to lose customers for sure, right? They might gain a few customers, but now I cannot use it. So anyway, getting back to this whole thing. So what I'll do is I'm going to list, the last maybe 12 or 14 bits or so. So 63, 62, 61, 60. And then I'll group these by 4s, okay? Because in this case, it makes it easier to convert the binary number into hexadecimal number, because each hexadecimal digit corresponds to exactly 4 bits. So when it's grouped by 4, it's easy to make the conversion. I don't have to kind of like do the grouping later on. So 59, 58, 57, 56, 55, 54, 53, 52, 51, 50, we'll do the entire nibble here, 49 and 48. Okay, so what these numbers are representing are the bit position inside a double, okay, which has 64 bits. The last one, the most significant bit, the one all the way to the left, is labeled 63 because we start counting from 0. Is that okay so far? Okay. So we want to understand what each part is for. Bit 63 by itself is the sign bit. If the sign bit is a 1, then the value being represented is negative. If the sign bit is a 0, then the number or the value being represented is non-negative. That's all we know. It can be 0. Okay? We just know it is non-negative. The next 11 bits, starting with bit 62 and all the way down to bit 52, these 11 bits. In the notes, it is simply called E, okay? And we'll talk about E a little bit later. But what you need to know is these 11 bits, as far as E is concerned, is an unsigned value. So the value of E can range from 0 all the way up to 1, all ones, 11 ones. So that turns out to be 2047. Is that okay? Okay, so remember, E itself is unsigned, okay, and the range of value for E itself is from 0 to 2047. The rest, I'll just label these things as M, which is not really the entire mantissa, but it is the fractional part of the mantissa, okay, because the 1 point part is implicit. If you want to look at the actual mantissa, it looks like this. Now this 1 and this point is never really truly represented inside a double. It is implied. But when you want to know what value is being represented, it's 1 point and then the mantissas times 2 to the power of E minus 1023 or 1023, because that is the bias according to the standard. Are we okay so far with this picture, or do we need? Are there anything here that I need to explain a little bit more? Yep.
Can you repeat the one again? The 1 point?
The 1 point thing?
Yeah.
The mantissas, bit 51 all the way down to bit 0, those 52 bits are the fractional part of the true mantissa. In other words, the value represented here, okay, this is the value that is being represented. The sign bit is either 1 or 0, so I'm going to use S question mark minus 1 colon 1 as a ternary operator to indicate the sign. If the sign bit is a 1, then you use negative 1 as the value of the ternary operator. If the sign bit is a 0, then you use 1 as the value of the entire ternary operator. Times Okay, so here's the part where the 1 point is explicit. I spell out 1 point, and then you have the entire m over here. But this is all binary. Okay, we're talking about binary numbers here. This is in base 2 times 2, which is not a binary number, to the power of e minus 1023. So this representation, or the value, the expression the value of a double, is in my notes, is on the Wikipedia page that I have a link to from my notes, and it is also here. So are there any questions about the value being represented? All right, okay. So what we'll do today is to look at a few examples, work it out in both directions. So sometimes I will give you a value to represent, and then we'll come up with a bit pattern, and other times I will give you the bit pattern, and we'll figure out what value it is representing. Yes?
When we're writing our code, it says when we're like trying to make the mantissa into like the maximum possible value of b, would it be like, for e, would it be just those 10 bits, or would it be the maximum value of the double?
Are you talking about m or
E.
E has 11 bits.
Yeah. So whenever you're like, wait, that was a mantissa, you're trying, I think I'm thinking of the wrong part.
The mantissa is the one that we want to use as many bits as possible,
Yeah.
because of the because of precision issues. When you're dividing 10, when you're dividing a small number by 10 and you can only store the quotient, you truncate a whole lot. Your precision goes down. So that's why we want to maximize the mantissa so that we lose as little precision as possible. But in the end, you still have to kind of do some shifting around so that the mantissa fits in exactly 53 bits, where bit 52 is the one that you have to chop. Okay? All right, go ahead.
Why is it e minus 10?
Because that is the standard.
Oh.
I cannot explain that part other than it is part of the standard. All right. Are we okay so far? Yep.
I think that numbers that's 1023 would be negative numbers.
Well, but then why not 1024? So I cannot answer that exact question why it is, why they choose 1023 instead of 1024, because 1024 is easy to subtract. You just turn off 1 bit and you're done. With 1023, you have to do the actual math in binary to get it done right. Okay. Any other questions about the value expression here? This is called the value expression. Is that okay? All right. So the next thing we'll do is to say, okay, how do we represent specific values? We'll start with something easy. We'll start with 1. Okay, which sounds pretty easy, right? I mean, how do you represent the value of 1 as a double? Okay, so what I'll do is I'm gonna do something that I can only do easily when I'm using physical paper. Just this. So I can reuse that portion. I can reuse the header. I suppose I can use a spreadsheet to do the same thing too. All right. So we want v to be exactly 1. Okay. So when you look up the equation, which is here, what do you think we should be assigned? Sign should be 0. Okay, cool. What do you think should be this mantissa here? So in other words, let's look at the entire mantissa. The entire mantissa is going to be 1 point. What do you think should be to the right-hand side of the decimal point? All zeros. Okay, very good. So, okay, bunch of zeros. I'm just going to use ... But remember, this is the only part that is represented inside the 64-bit of a double. The 1 point is implicit. It is never represented. Are we okay? Next, what do we do with the exponent? In other words, 2 to the power of e minus 1023. What is this whole thing supposed to be? I got 1 here already. So this whole thing needs to be 1. The entire thing should be 1. Okay, so I want this entire thing to be 1, which means we need e minus 1023 to be 0. Okay, so e minus 23 should be 0, which also means e should be 1023. All right, cool. So now that we know these various parts, let's flip back to the mapping of the bits. Okay. So where do we throw these individual bits into? The sign bit goes here. That's a 0. E, which is 1023, needs to go here. Now e is 1023, which is fortunately a power of 2 minus 1, because 1024 is 2 to the power of 10. 1023 is 1 less than that, which makes it very easy to figure out. 0 and then all ones. Very good. Good job. Okay. So we have a 0 here, and then we have all ones. Oops. Like that. All right. What else? We didn't figure out m, but we already got it figured out, because m, or the fractional part of the mantissa, should be all zeros, because the 1 point is implicit, so that means the fractional part should be all zeros. Are we still doing okay so far with this picture? So now we have to figure out, okay, so what is the hexadecimal representation of this? And because the bits are already arranged by groups of 4, we got a 3 here. Okay, that's a 3. This is a F. This is another F. And then these are all zeros. Okay, so we just have a whole bunch of zeros down here. So in other words, when you're done with this homework assignment, if I give you 1 as the argument to the entire program, I'm expecting D, the unsigned 64-bit integer. When I print it out, it is supposed to be 0x hexadecimal 3FF followed by all zeros, 13 zeros in this case. Is that okay? Well, I claim that this is the representation. What are you guys supposed to do?
Just to show us.
Okay, we have to prove that this is the case. So the easiest program that I can write to do this is really just to say, okay, this is main.c. We have the pound include stdint.h. If you don't know anything about stdint.h, what do? Google it. Exactly. When you Google standard integer.h, you will find the actual definition of that header file, and then you will find the names of the types. You will find the range of the numbers as macros. Okay, so that can be helpful when you're doing your homework assignment, so that you don't have to figure out, oh, so how do I compute the largest value that can be represented by an unsigned 64-bit number? It's already there. Okay, so that's why this file is really important to include. I would even argue that in your other classes, in many cases, you should use standard integer, because you should know the range of the values of the variables that you're dealing with. So as a result, you, the programmer, really should choose, do I need a 32-bit integer here, or do I need a 64-bit integer here? Should it be signed, should it be unsigned, and so on? You have to make that decision. All right, so we have main, and it has a u in 64_t, d just like your homework assignment. I need to do something with d, otherwise it gets optimized out of the executable. So this is the smallest program I can write, and I'll just be even more lazy here and put a label here. Just so that it's easy to set up a breakpoint when I'm getting into the debugger. Okay. So here we have, oops, I don't want to encrypt it, just want to exit. GCC-G to include debug information, -O to name the output executable file name, and then another -1 all to make sure that I don't make any stupid mistakes. Pedantic is not needed here because this program is so simple, there's no way that it is non-compliant to ANSI. So the last one is just the name of the source file. Compile, it complained about label L1 is defined but not used. It complained about D is set, which means it is initialized but not used. Both of these are explainable because of the way that we plan to use this program, so they're okay. All right. So now we use GDB to debug the program, set up a breakpoint at main:_L1, just like how I would grade your program, run it, and now we're at a breakpoint. So at this point, we can say set var d equals 2, and oh, I don't need to cast it because I know exactly what it is supposed to be. So I'm going to switch back to the document camera for just a moment here, because I want to look at this, and remember this is 3FF and then followed by 13 zeros. Okay, so that's exactly how we'll put it here. So d equals to 3FF 0, and then 12 after this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. I can double check print /x, which means I want to use hexadecimal to print d. Okay, I get back what it is supposed to be. Now is the trick. Dereference the pointer, which is a double, the address of a double, but I'm casting the address of d into an address of a double and then dereference it. In other words, here's the address, but do not look at the content at this address as a uint64, but instead look at these 64 bits as if it is a double. Okay, because then the debugger is going to interpret those bits as a double and print out the value of those bits as a double in base 10, and it turns out to be 1. Woohoo! All right. Are there any questions about this part of the demonstration? Because this is a very simple experiment, but it shows you basically everything that you need to know to get the homework assignment done and also study for the exam on Thursday. Are there any questions? No questions? This is all good? All right. So let me give you a super duper challenge here. How do I modify 3FF followed by all zeros so that it will now represent, oh, I don't know, -4?
How you would change?
So to turn this into a -4, okay, let's switch back to the document camera. What would be the easiest thing that okay, we need to adjust that. The sign, right? Okay, let's deal with the sign first. The sign needs to be turned into a 1 because now we're dealing with a negative value. Okay. What about E? We're trying to represent 4, but we have to coerce the value of 4 so that it becomes 1 point blah 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 times 2 to the power of something. Let's deal with the 1 point blah 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 first. Okay. Do we need to specify anything other than zeros to the right hand side of the binary point?
It needs to be a e to the 1.
Hmm?
The exponent needs to be a 1.
The exponent needs to be a 2. Okay, so let's work this out entirely. Okay, so I'm gonna take it out. Okay. All right. So we'll look at the value first. Okay, so we'll look at the value equation first. So we are dealing with the sign being a 1 because we want the value to be negative. M is 1 point all zeros, and then we also want 2 to the power of e minus 1023 to represent 4. Okay, if 2 to the power of e minus 1023 is supposed to equal 4, what is 4? 4 is 2 to the power of 2, right? So that means e minus 1023 is 2, which also means e is 1025, 1025. Is that making any sense? Okay. All right, so I think we got all the parts. So when I flip this around and they go like, okay, what should go into the sign? Okay, that's supposed to be a 1. What goes into the mantissa, or the fractional part of the mantissas? All zeros, just like last time. Cool. Okay, so what is changed in this case, really, other than the sign, is e, because e used to be 1023 because the actual exponent of 2 was supposed to be 0. This time it's supposed to be 2, which means as a biased number, it needs to be 1025. Okay, it's not 1 less than the power of 2 anymore. We have to go through a lot of calculations. Nope, because now it's 1 more than a power of 2. Okay, 1024 itself is 2 to the power of 10. Okay, which means it is 1 followed by 10 zeros. Plus 1 means the least significant bit is also going to be a 1. So that means these bits will be 1 followed by all zeros and end with a 1 here. That's it. So now you group it to, in groups of 4 and then convert it into hexadecimal digits. This one is a C, this one is a 0, this one is a 1, and then we have all zeros after that. Is that okay? So the hexadecimal representation is C, 0, 1, and then all zeros. Yes?
How do you know that the last bit in the E section, how do you know it's 1 again? Bit 52, how do you know?
Because you convert 1025 into, this is in base 10, right? It is 1024 in plus 1. Is that okay? 1024 in base 10 is 2 to the power of 10 plus 2 to the power of 0. Right? And that's how we know, this part is 1 followed by 10 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this is just 1 here. So we end up with 6, 7, 8, 9, like that. That is how we do the conversion. Okay? So are we good so far? Let's go back and check this code. C010 and then a whole bunch of zeros. So we go back here and then we set the variable D now to C01 and then 13 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3. Okay? And print coerce the interpretation of those memory addresses. Now we have -4. Are we doing okay so far, or is that good? Okay? Say that one more time. Say again?
With an odd number.
With an odd number? Let's try something that's worse than an odd number. Because every odd number is not exactly an odd number. It depends on the scale. Okay? All right, so another example. Okay, so I'm doing some work in the background here. Let's try something that seems pretty nasty. Okay, so we'll switch back to this part here. I mean, is this helping?
Yeah.
In a way? Okay, good. And as I said in the previous class, if you want to, you can do a screenshot of whatever we talked about today, or massage it, put it into a Word document by yourself and bring it to the test. Okay? Anything that's either printed or handwritten prior to the test, you can bring it. Okay? Doesn't have to be your own material. It can be my material. It can be a material that you find somewhere on the internet. They're all fine. Okay. So once again, we start with V. So this time, let's pick something that is kind of seemingly difficult to deal with. Let's try, I don't know. Let's try 18.375. Okay. Is that okay? Does that seem kind of challenging? Trust me, this is not challenging. 18.1 is very challenging. This one is not. Okay, so this is what we want. So now we need to break it up into the 3 parts. We need to break it up into the sign part, which is the easy one. Are we dealing with a negative value?
Yeah.
No. So that means the sign bit is going to be a 0. Okay, so that's the easy one. Let's look at the entire mantissa and also look at the exponent. What do you think is going to be the e minus 2 to the power of e minus 1023? What do you think that should be represented? In other words, I know that my mantissa is supposed to be 1 point blah, 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 right? What is the power of 2 that is less, what is the largest power of 2 that is less than or equal to 18.375?
16.
16, very good. How do you express 16 as a power of 2?
4.
It's 2 to the power of
4.
4. Okay, very good. Okay, so this is we want this equality, right? We want so we want e minus 1023 to be 4, which also means e has to be 1027. Is that part okay? All right.
Explain that one more time. Explain it one more time. I kind of.
Okay. So this quantity is basically dealing with the magnitude of the value that we are representing. The mantissa, you don't have a choice about the actual mantissa. It has to be 1 point something. So in order to use the exponent of 2 to only account for the magnitude, but the actual value is specified by the mantissa, you need to find the largest power of 2 that is less than or equal to, in this case, 18.375, which turns out to be 16, which is 2 to the power 4. Is that okay? Yeah. All right, cool. So now that we know that we're dealing with that, what we need to do next is to say, okay, now how do we express 18.375 divided by 16? Well, that's going to be difficult. I'm not going to deal with this. But instead, what I'll do is I'm going to take a look at 18.375, convert that into binary first, and then we'll divide it by 16 by shifting the binary point. Is that okay? I'll say it one more time. So instead of doing this division first and then look at the result of the division and then convert it into binary, I'm converting 18.375 into binary first and then do the division later. Because division by 2, each division by 2 is a shift. And shift is easy because all you're doing is to move the decimal point from one place to another place. Is that okay? All right. So now we look at 18 and we go like, okay, 18.375, how do we express this as a sum of powers of 2? That is basically what we're looking for. Okay. In other words, remember the currency example that we used in class and how I said if you know how to deal with currency, you know base conversion. Same thing here. So remember, you have currencies of the face values of 1, 2, 4, 7, 1, 2, 4, 8, 16, 32 on one side, and then half, quarter, eighth, 16th on the other side. Okay, those are available to you. Is that okay? So now the question is, how do we select the bills and the coins so that we can represent exactly 18.375? That's the question. So where do you start?
The largest.
The largest, okay? So it looks like we got a 16, right? Once you get the 16 done, we got a 2 left. And then we don't have any halves, right? We have a quarter. Once we take up the quarter, we have an eighth. Does that make any sense? Are these all powers of 2? 0.25 is 2 to the power of negative 2. 0.125 is 2 to the power of negative 3. So in fact, they are all powers of 2. I didn't say anything about the power of 2 has to be on the positive side. It can go negative. Are we doing okay so far with this? So when you convert it into a binary number, it becomes 1, which is for the 16. Okay, we can do it really step by step. 1, 2, 3, 4, plus the 2, which is just a 1, 0, plus the quarter, which is 0.01, because this 0 is the half, and then plus 0.001 because of the eighth. Is that okay? So you add up all of these digits, 1, 1, 0, 0.01, and then we got 0, 0, and another 1. So we got the binary representation of 18.375 to be 10010.011. It's a binary number. Are we doing okay so far with that representation? Sound good? All right. So now we need to look at this number and go like, but the mantissa cannot be this. The mantissa has to be 1 point something, okay? But we got that part done already. We already figured out the power that we need is 4. So that means it is now time to shift this binary point 4 times to the left. 1, 2, 3, 4. So the point actually belongs here. Is that okay? So the mantissa turns out to be 1 point. Okay, I'm just going to copy from here. 0, 0, 1, 0, 0, 1, 1. Yep, I think that is the case. Are we still doing okay so far? Yes? All right. So now we look at all of these things that we have collected, and then we flip the sheet over to the other side so that we can actually write down the zeros and ones. The sign bit is a 0, put a 0 here. The exponent is 1027 or 1027, which is 1024 plus 3. Is that right? This is 1024. This is 1. This is 2. 1024 plus 2 plus 1 is 1027. Fill the rest with zeros. So in the exam, I'm not going to trick you guys and use an exponent that will have kind of random zeros and ones, turned on. I'm going to give you something that's easy to figure out, like this one. Okay, you might be able to find that your scientific calculator is also capable of decimal to binary conversion and back. Okay, that can be helpful too. What about the mantissa? Well, the mantissa turns out to be a little bit more complicated this time because we are not representing the entire mantissa, we are representing only the fractional part of the mantissa. So that means we're dealing with 0, 0, 1, 0, okay? And then 0, okay, I need to make sure there's enough room. 0, 1, 1, and then a whole bunch of zeros after that. So are we still doing okay so far as where the parts go back into the 64-bit representation? Is that okay? All right. So now we look at groups of 4 bits, convert those into hexadecimal digits. So we got a 4 here, we got a 0 here, we got a 3 here, we got a 2 here, and we got a 6 here. As I said, I will give you the table to do the base 2, base 16 conversion, but it is best that you put that table on a separate sheet of paper so that you can just take that paper, put it side by side with your actual test, so you don't have to flip between the pages all day long. Yep.
So when you move the decimal to the left, do you change the E?
No, the E is already adjusted. I'm just accounting for the E, so by doing that.
Okay.
Yep. Because before the binary point is shifted, which is when it's here, it is implicitly multiplying 2 to the power of 0. But when you already have 2 to the power 4, you have to make the mantissa itself 1/16 of what it used to be, and that's the action of moving the binary point to the left by 4 places. Okay. All right. Well, it's time to check whether this works or not, right? So we go back to here, and then we say, okay, let's change this number this time to 40326, and then we have 11 zeros in this case. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then we take a look at the double, the value represented by the double that has the same bit pattern, and it is exactly 18.375. So are we doing okay so far, or are there any questions about this? This is okay?
Were we gonna do anything with the 16 as a division, or was that just for shifting?
It's only determining how many times we have to shift, and therefore it also explains what goes into E. Is that okay? Now I can flip this around and ask the question of, okay, so at this point I have been working out the bit pattern given the value that I want to represent as a double. But I can ask the question in the opposite way. I can give you the bit pattern, and then you figure out what value it is representing, right? So I'll be very lazy here, okay? And I'll give you this number. So I'm turning the 4 into a C, and I'm turning this 2, or this, yeah, I'm turning this 3, not the 2. I'm turning that 3 to a 4. and then keep the rest. Okay. All right, so looking at the difference between this integer versus the one that we had before, can you figure out the actual value represented by the double without going through all the different bits and whatnot? What do you think? So let's figure out. When I changed from the hexadecimal 4 to a C, what is being changed? Which bit got changed? There's only one bit that got changed from a 4 to an 8. The sign bit, very good. The most significant bit got changed. So the most significant bit was a 0, now it is a 1. How would that impact the value being represented? The sign bit is now a 1. Is a negative value. Very good. Okay, so the value being represented is now negative. Good. I also made a change here. I made a change from
3 to 8.
this 3 got to 4. Okay? So this 3 is a part of what? It is within the most significant 12 bits of the 64-bit number, but we know the most significant bit itself is a sign. So that means this 3 now becoming a 4 is a part of what? Sign, E, or M?
E.
E. Very good. And by how much did I change? 1, right? So that means the magnitude is changed by, how did I change the magnitude represented? By increasing the exponent by 1. It's an exponent of 2, but by adding 1 to the exponent of 2, how am I changing the power of 2? Okay, am I adding 1 or am I doubling? I'm doubling, okay? So the quantity, or the scale, not the scale, but the unit is now doubled. It used to be 16, remember? We used to have 16, e to the power of 4, which is 16, as the magnitude. Now it's going to be what? 32, okay? Which means I'm just doubling the value. Did I change the rest? In other words, did I change the fractional part of the mantissa? Nope, because the fractional part of the mantissa starts with this 2, the 6, and then everything to the right-hand side. So that means the mantissa itself was not changed. I just changed the scale. Okay? It is 1 point blah, 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 blah. It used to be times 16. Now it is times negative 32 because we also changed the sign of the number. So if we know that it used to represent 18.375, what is it representing now? It's negative 36.75. All right, so let's try that. Set that, print it, and it's exactly negative 36.75. So I might give you a question like that, okay? I will say this particular hexadecimal representation, which is only representing the zeros and ones, is representing this value. We know that already, okay? But by changing the bit pattern from this to this, what is the new value being represented? I might ask a question like that, so that you don't have to start from scratch to do all the base conversion and whatnot, but you have to notice what is changed and how that change is going to impact the value being represented. Is that okay? Or I can change the question around and tell you that 18.375 is represented using this particular bit pattern. Now I want to find out what is, I might times 4, right? And then ask you, what is the representation of this value times 4? Which is about the same kind of question. In other words, I will tell you that we know 18.375 is represented by 40326, all zeros in hexadecimal. Now tell me how to represent 73.5, which is doubling the value again. Okay? So that way you don't have to rework the entire thing, but you do have to separate the parts out, find out which part needs to be tweaked and how to tweak it in order to get the result done. Are we doing okay so far with this? Is it helping with your understanding of double? Okay. This is also something that you can do on your own. Okay? You can just pick some, yeah, go ahead.
Just a quick question. So the 0.375 changes to a 75 because when you go from a 3 to a 4, the whole thing doubles, right?
Yes.
Okay.
So when you look at 18.375 and that number times 2 is 36.75. And you are allowed to use a scientific calculator in the test. So you can actually calculate the ratio between two numbers. Yep.
On our program, how do we like separate it into 4 separate bits in order to create the ANSI?
You don't, because you only need D to be a binary number. My program, my test script, will do the print /x in order to print everything in hexadecimal. So you don't have to do base 2 to base 16 conversion
Okay.
in your homework. But in the test, you will have to do it by hand. Okay. Any other questions? Yep, go ahead.
One kind of, would you be willing to show us what the 0.1 would look like if we
Say that one more time.
if we did 0.1 and tried to convert that?
0.1?
Yeah.
Okay, so let's do it by hand first. Okay, let's try to kind of do this by hand because it's not easy. Okay, so we'll flip to another page here. This is going to be complicated. We can work out a few bits, but we won't be able to figure out the entire thing is repetitive, so we can actually work it out. But it's not fun. So the value that we want to represent is 0.1. Oh, okay. So the value that we want to represent is 0.1. So I'm going to flip this back to this one here so that we can see, okay, the value we are representing is 0.1 in base 10, which is 1/10. And we know the sign is easy. It's a 0 because we're representing something that is non-negative. E 2 to the power of e minus 1023 is not too bad either because we just have to find the largest power of 2 that is less than or equal to 0.1. Well, that's not too bad. Okay, so 0.1, you have to basically say 0.1 is greater than or equal to 2 to the power of what? Okay, and just barely greater than or equal to. We know -3 is not going to work because -3 will give us 0.125 in base 10, so it's probably a -4. Okay, is that okay? All right, so now that we know 0.1 is greater than or equal to 2 to the power of -4, and it cannot be 2 to the power of -3, that means this is the value that we want. So e minus 1023 is going to be -4, which also means e itself is going to be 1019. There we go. Okay, so that part, we got to figure out. The mantissa is the difficult part. In other words, if I were to convert 0.1 into a base 2 number, it's not easy. Okay, so let's not deal with 0.1 then. Let's factor in that we already have a shifting of the binary number. So we are dealing with 16 times 0.1, so we are looking at 1.6 and in base 10, and we are trying to convert this into the mantissa format of 1. Blah 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 in base 2. Is that okay? Does everybody understand why I'm converting 1.6 in base 10 into 1. Blah 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 in base 2? Because when the exponent is already adjusted by -4, that means in order to represent the same value as 0.1, I have to now multiply the mantissa by 16 to account for the magnitude is already e to the power of -4. Is that okay? Okay, let me explain it in the equation. Yep, go ahead.
So when you have a positive exponent, you divide, right? Like when you have positive exponent,
Yeah.
then you divide, and when you have a negative
Correct.
one, you multiply, right?
Yep. So we originally had 0.1 times 2 to the power of 0. Now that we know the exponent that we need is -4, we now have to adjust the whole thing by saying this is 16 times 0.1. Is that okay? Is that equality established? The 16 cancels out to the power of -4. So we get the 0.1 back. Okay? But what is 16 times 0.1? We get 1.6. Is that okay? So now you have to think in terms of the McDonald's employee again. You have to make change for $1.60, but you're using base 2 currency. Okay? So now what do? Well, you do the usual thing. You say, this is 1 plus 0.5, right? We don't have any 0.25. We don't have any 125, but we do have one of those 1 divided by 16, or 2 to the power 4 here. And after that, I can't really track using by hand. So what we'll do, I'm going to cheat here, okay? Because you guys asked me this question, and I told you this is not going to be easy, right? So I'm going to cheat and use a spreadsheet to do the rest. Best part of using a spreadsheet is I can share the spreadsheet with you guys after the fact. So I'm going to make a new spreadsheet here. Spreadsheet, come on, new spreadsheet. And I'm going to name the spreadsheet after today's date, so this way you know this is about the content of today, which is also a part of the video name. So we'll rename it as 2017-0926 cisp310. There we go. All right, so we're looking at 1.6, and we want to convert 1.6 to a binary number. So what we need to do is to set up, one column that has powers of 2. Okay. Powers of 2. We'll start with 1, and then we'll do the half of the one before. Now we can just go like, oh come on, that. Is that okay? It's a trick, in spreadsheet, how to use a spreadsheet, and I think all computer science majors really should know how to use a spreadsheet. It would be kind of interesting if I find a conversation between a computer science major and a business major, and the business major is talking about, oh, look at all these things I can do with a spreadsheet, and the computer science major go like, I have no idea what you just did. That would be bad. Very bad. Okay? Because after all, a spreadsheet is a gigantic calculator that can even automatically figure out the dependency between the equations and all the formulae, so that when you update something, it will automatically update the rest. It will figure out the dependency. It's kind of like the combination of a calculator, the make utility program, and a table. Because the make utility program is dependency based. It will figure out, oh, this is the executable. You just updated this .h file, okay? And what needs to be recompiled, what needs to be relinked. It will figure out the rest and then give you the executable in the end. Okay. All right, so what we'll do here is we're going to ask the question. Okay, so we'll say, is this number greater than or equal to this number? True. Wow, profound. Then we'll say, over here, we'll say, okay, you can actually use if in a spreadsheet. So you'll say if this, okay, then we are talking about this value minus this value here. If not, it is just this value by itself. So in other words, we're tracking what is left to do. Is that okay? So over here, we can just drag this down by 1 to figure out, do we have a 0.5? And over here, we can drag it down by 1 because once you take care of the 0.5, we have 0.1 left. Over here, we drag it down and say that, nope, 0.1 is not greater than or equal to 0.25. But then you also have to make sure that after this point, you kind of have to drag it all at the same time. There we go. So, because of the limitation of how many of these rows I can fit in the screen, I'm just going to stop here. And then people will ask, where's the binary number? You promised us a binary number. Where is it?
The
default.
Yeah, true.
Column D. Yeah, column D is our binary number. Where's the decimal? Where's the point? Okay, if I were to draw a line, a border, okay, this is really cool. This is why I like spreadsheets. This is the point. So if you look at the number sideways like that, then you get 1.1001100110011, and so on. Yep. Questions about this? Any questions? No? Okay. So is that okay? I mean, are we getting a general idea of how to convert from base 10 to base 2, even when it has fractions? The principle never changes, okay? Whether it's a whole number, an integer, or whether it's a fraction, stuff like that, it's still the same thing. You're really just looking at the remaining portion of the value and say, let's look at the next power of 2. Do we have at least one of those things? No, okay, move on. If you have at least one of those things, take it, subtract whatever the remaining amount is from that amount, and then you get the rest, okay? So what I'll do now is I'm going to share this with the whole class. In fact, I will share it with anyone on the web. How about that? If you want to convince your 5-year-old or 6-year-old sibling that binary is the way to go and they should promote this in an elementary school, your kid brother now has access to this spreadsheet. Okay, so then we'll go ahead and click share and copy link and then go back to Canvas. I was just about to say Moodle, but nope, Moodle is no more, so almost no more. Okay, so we'll add here and just say spreadsheet of 2017, September 26th. Put the link here. Yes, you might need to right-click and select right-click and open link, but I'm lazy. I'm lazy. There we go. Okay. So what have we learned so far? We're not done yet, are we? Because now we need to put this into the debugger and test it. Okay. All right. So going back to the debugger, which is here, we first have to figure out what bit pattern we need to feed it. Okay. We know the number is not negative, so this is not going to be a C. But we also know, okay, I'll give you another trick here. It's kind of a cool trick. All right. Do we know what is the exponent that we're dealing with?
4.
Okay, we know it is -4. -4, okay? So that means E itself is going to be 1023 minus 4, right? Okay, let's do some typecasting here. I'm going to cast this as a UN64_T so that everything is now a 64-bit number. How many times should I shift to the left in order to put this at the right place, so that bit 0 of this value will end up as bit 52 of the representation? Shifted by 52 times. Okay, so shifted by 52 times. Okay, what about the mantissa? This is bitwise OR. And we'll use extra parentheses just to make sure that we get this part done right. Okay, what about the mantissa? Okay, let's go back to the document camera because we got all that math. Oops, not the document camera, but the spreadsheet. Okay, so when you look at the mantissa, it's everything from the second row and down. Okay, we are talking about this stuff here. Okay, because the 1 point is implicit. Okay, this is the fractional part. So when you look at it sideways, it looks like 0110. Excuse me, the other way around. 1001. 1001, and seems to be repeating itself. Okay, what is 1001 as a hexadecimal digit? Okay, 1000 is an 8 plus
So
1
it's a 9.
is a 9. Okay, very good. So we got 9. So that means we got 9s for the rest of this hexadecimal digit number. But do not put in a whole bunch of 9s without the 0x prefix, because otherwise it becomes decimal. Now it is hexadecimal. And how many 9s do I need? In other words, how many hexadecimal digits do I need to make up for 52 bits? 52 divided by 4 is 13. Very good. Okay, so we need 13 of those things. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3. Okay. So I'm going to claim that this is going to give us the right representation for the value 0.1 in decimal. Okay, press the enter key. Double check it first, right? So we want to double check and make sure that this number is indeed what we want. Okay, it says it's 3FB 99999. Okay, let's double check. Is 3FB really representing -4 as the actual exponent of 2? We know 3FF is 0 from early on. Okay, so 3FF is 0, 3FE is -1, 3FD is -2, 3FC is -3, 3FB is going to be -4. Now I was looking at you the whole time. Was it 3FB up there?
Yeah.
Okay, because I do not remember. It was actually 3FB. I was just double checking. Okay. Some other professors have everything prepared ahead of time before the class, so they can actually regurgitate and actually just just say something they have memorized. I cannot remember anything that is more than 5 seconds ago. So I was looking at you guys, not looking at the screen, so that I can count backwards and see if I can come up with 3FB to represent -4. So that works out. The E part works out. The rest are all 9s, but they're hexadecimal digits, so they're not decimal digits. So now the moment of truth is to say, if I look at these 64 bits and interpret the 64 bits as a double, is the value represented by the double 0.1? That is now the question. Okay. And darn close.
Close it's gonna get.
Pretty close, yes.
So it'll never be exactly 0.1 because.
Well, let's find out whether it can be exactly 0.1, because the other way to do this is to use set var d, not d, but we'll reverse it, right? We'll specify what we are storing, being 0.1 as a double. And then we'll print the integer out in hexadecimal. Do you see what I'm doing here?
Yeah.
So I'm actually specifying the value I'm representing in double by storing using this technique instead of printing using this technique. And then I will print it out using the other technique, which is print/x, print in hexadecimal, just d itself, and it's off by 1, rounding. But we also want to know whether it is now known as 0.1 or it is still, there we go. So it's off by a little bit too, but not by as much as my representation, because in my representation it is off by, okay, are we talking about the same number of digits here? No, mine is better.
There's no precision here.
Mine is actually better because mine has one
significant
more
bit.
place, so it's only off by 0.8 of this amount.
That's off by
So
0.1.
mine is actually closer. Yes. Only by a little bit, but it's close. So are we doing okay so far with all this exercise? It should help you with your homework as well, because now that you know what each portion of a double is doing what, and how to do the conversion by hand, then it is up to your algorithm to do all the conversion. But the algorithm is already in the class notes. I just did not spell it out like pseudocode, because I think you guys can understand the text and then turn it into your own logic. Is that okay so far? Okay, any other examples you want to illustrate? What if I were to ask you about the representation of 512? Go like, why do you have to pick those values? 512 here, that doesn't sound very good at all. Because 512 is 2 to the power of 9. So you know that the mantissa is going to be 1.0s, right? You only have to adjust the exponent to get the magnitude correct. So you need a magnitude to indicate 9, which means E needs to be 1023 plus 9. So now you only have to figure out what is 1023 plus 9. Well, fortunately, 1023 plus 9 is 1024 plus 8. Can you buy that? Okay. 1024 is a base is a power of 2, so is 8. Yep. So it'd be 1 followed by 10 zeros plus 1 followed by 3 zeros. Okay. You put those ones at the right places, fill up the rest with zeros, do the, every 4-bit is a hexadecimal digit conversion, and you're done. Is that okay? So I'm only verbally describing because, if you want to do it by hand, you can just kind of try to do it by hand. Is that okay? So as it turns out, things that we think are easy, like 0.1, turns out not to be very easy. But things that we think is kind of difficult, which is 512, turns out to be pretty easy.
408, all zeros.
Sorry?
408 by all zeros.
Yep. Let's try that. Very good. Good job. You did a conversion really quick. Okay, so it's 408 and then a whole bunch of zeros. So at this point, I'm not going to put in the zeros the way I used to do it. I'm just going to shift it, right? By how many places? How many zeros do we need to pad to the right-hand side? 52 zeros, right? That will pad it by 52 zeros. Well, we double check first. Yep, looks right to me because, when you look at these numbers, they align. They're off by 1 because of the $10 versus the $8. And then we look at the double representation and what value it is represented as, interpreted as a double, and it is 512. Good job. Excellent. Are we good so far? What about 513? Well, 513 as a binary number is 1 followed by 9 zeros plus 1, right? Yeah. So you just have to figure out where the 1 is and then where it's going to be in the mantissa, tweak that 1 nibble corresponding to that 1 that is now new, and then call it a day. Is that making any sense? Yep.
Would the last one be part of the mantissa instead of the exponent?
Okay, so this is what we're going to do. Okay, so we look at, this, I can just reuse this part here. So 513 is 512 plus 1. Which is 1 followed by 9 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, plus 1. So we are looking at 1, 0, 1, 4, 5, 6, 7, 8, 1. Right? We already know the representation of 512. So we need to look at, put a point here. And we know this is the first nibble after the exponent. This is the second nibble after the exponent. This is going to be this, right? So this is the third nibble after the exponent. And it needs to be turned into an 8. Is that okay? So what we do is we'll give it a try. We'll give this a try. And this time we kind of have to spell out a little bit more. So we have 0, 0, 8, and then filled up the rest with zeros again. So we got 6 already here, so we need what?
Shift by 40.
Yeah, we can shift by 40. And then look at the double. 513. So this is what you can do, to kind of help practice and understand the base converting between the scientific notation and in the double representation. Okay, I'm not going to assign any work because I'm not going to grade it. Okay, but it is something that you can do. Okay, you can just think of a number. Don't think of something that's too fancy. Okay, but think of a value that you want to represent as a double. Figure out the bit pattern, and use GDB to check it. You can also do it the opposite way. Give yourself a bit pattern, and then use this technique to figure out what value it is actually representing. So all of that is going to be helpful to help prepare you for the exam as well as your homework assignment. Yep.
And how many bits did Google allow you to use on the spreadsheet? Because you could like write it in hex and then convert it on that, but how many bits does it allow again?
It's not a whole lot. I think for binary to, if you look up, if you look up dec to min, it has a very limited number. So it didn't say here, but if you go to the help, it will show you how many you can deal with. So for this function, the value has a maximum of only 512, 511, and negative 512. So it's not a whole lot. You basically view 10 digits in binary, and that's it. Yep.
Can you go over, like, represent the bit pattern to a double and actually write it out?
You're reversing the process. If I give you a bit pattern.
How would you do that, like, if you were to write it out?
Okay, so let's try this one. Okay, so let's try out 0x C, B, B, okay, B. So let's try B. We'll have some fun here. BFF, how about that? Okay, no one in this class is going to use the word, the phrase BFF, but here we are in hexadecimal. It is 3FF. Okay, and then we'll figure out the rest. We'll give it something fun to do. Okay. Okay, how about DAD? DAD, and then all zeros. Trust me, my kids definitely do not think of me as BFF. Just watch Star Wars and you ask the question, do you think Luke thinks of Darth Vader as BFF? Maybe after Vader is dead. He'll go like, yeah, I guess Dad did save me once. But you know what? I lost my hand too, so. All right, so when you look at this, then you figure out the bit pattern first, right? So you put this thing here, and trust me, if you want to, you can do a screenshot of this. If you don't want to make your own, you can make a screenshot. Just use the GIMP or something, crop out that portion, print it out on a piece of paper. You can bring it to the test. I don't mind. I'm referring to this thing here. Seems pretty useful as a template. Okay. So B is 1, 0, 1, 1. Okay, so we got 1, 0, 1, 1. F is 1, 1, 1, 1. Okay, that's easy. 1, 1, 1, 1. And then D is a 1, 1, 0, 1. And then we got 1, 0, 1, 0, and then another 1, 1, 0, 1. And then all zeros after that. Okay. So when you look at this, you say, is this a negative number? Oh yeah. It's going to be a -1 times something because of the sign. And then this E is pretty easy to figure out. It's all ones. Okay? Except for the first 0, which means it's 1023. If E is 1023, what is the power of 2 that we're actually dealing with? 0. Okay, so times 0, or times 2 to the power of 0, which is 1, times 1 point. Okay? Now we need to copy the tedious part, which is 1, 1, 0, 1, 1, 0, 1, 0, 1, 0, 1, 0, 1. Okay? But that's base 2. So if you want to convert it into base 10, then you just say it's -1. This is canceled out because 2 to the power of 0 is just 1, times, okay, this is 1, plus 1/2, plus 1/4, no eighths, a 16th, and then the pattern, it becomes 32. No 64. There's a 128. No 256. There's 512. There's 1024. There are no 2048, but there's 4096. That should be the answer.
This is where a calculator would begin.
Or if you write it out like this, I will give you full credit.
Oh.
Yep. So you don't have to go through the actual tedious part to convert this into an actual number. If you can show me that this is the value, I'll give you full credit for this. Because punching it into the calculator and figure out all those decimal places is kind of tedious. I don't want you guys to do really, really tedious work. Is that okay? But here's the part when you have to say, really? Let's check it. So we'll go ahead and go back here, and then we set the var to, this one is easy to represent, 0x BFF dad 1 2 3 4 5 6 7 8 9 10. There we go. And does that look like the value? Okay. Well, maybe. Okay. Well, that's okay. We can figure it out. Okay. So it's 1 divided by 2 plus. The problem with this is I have to cast it every single time. Do I have to? Yeah, I think I have to. So double 1 divided by 4. 1 divided by 16. I can work out just a few just to give you an idea of, yes, that is the value. Okay, one more term. Okay. The next one is 128. Okay, plus the 1. Okay, fine. There we go. So it is close. I didn't finish the whole thing because I ran out of patience. Is that okay? Sort of? So did I answer your question of doing it the opposite way? Yeah. Cool. All right. So we are running out of time. I'm going to go to the lab. So for those of you who are still working on the program to convert from the base 10 scientific notation to the double 64-bit format, you can ask me questions during that session. But there are no additional questions. If you have any questions about the test itself on Thursday, you can also ask me those questions during the lab time. Yep? If you need to bring a writing instrument, I would bring spare sheets of paper, like binder paper. That's about it. Those are the only things you
I missed the day, so this was really good. They basically did the same thing before,
The same
right?
thing, yeah, pretty much. But he actually went through the
Yeah, they actually kind of go over that.
Yeah.